Good afternoon. Welcome to today's lunch hour lecture. But before I introduce Dr. Jason Lotay, I tell you that on next Tuesday, the lecture is Women Against Pit Closures. The lecture is entitled Women in the Miners' Strike of 1984-85. But for today, Jason is in the maths department. He's been here since 2011. And before that, he has 2 degrees from Oxford. He spent time in America, back at Oxford, at Imperial, and now he is here as a reader. And today, he's going to be talking about travels in the 7th dimension. I should just mention to you that we have Slido here, event code 7786, and Emma here will be manning them. After Jason has finished his lecture, there will be time for a few questions, and mics will be provided, so please use those. Thank you.
Thank you very much. So, welcome everyone to my adventures in the 7th dimension. And I think it's safe to say this sounds a bit like science fiction, so I think it's only appropriate that my titles do this. But actually, as was said, I'm a mathematician. So what I want to tell you today is about 4 questions. What is the 7th dimension? Why 7? Why not some other number? What do we know about the 7th dimension? And then, what do we still want to find out? So as I was preparing this lecture, and I was thinking about the first question, what is the 7th dimension, I thought, Google must know the answer. Right? So I stuck 7th dimension into Google, and what came up was a radio show on BBC 7, a conspiracy theory film a bit like the Da Vinci Code, and the cult classic, The Adventures of Buckaroo Banzai across the 8th dimension. They got the numbers slightly wrong, but otherwise it is fine. Okay, but actually, when we think about the question, what is a dimension, we don't have to go into outer space to think about this question. We can actually have a much more mundane situation in life where we talk about dimensions all the time. And that's when you're buying furniture. So when you buy furniture, you need to know that it's going to fit in your room. So you need to know its height, its width, and its depth. The usual 3 dimensions that we know. But of course, there are many other factors that go into buying a piece of furniture. For example, if you have to carry it up the stairs, how heavy it is very important. And that's something that we can measure, the property of the wardrobe. Also, a classic extra dimension that I'm sure you've thought about is time. What's time got to do with wardrobes? Well, there's the time it takes to build it from flat pack. It might take a while, might affect your consideration. All the time it takes till it gets delivered. It's another way which you might think about it. There are also less obvious things that we can also measure. For example, the color of the wardrobe. So we don't usually think of color in terms of numbers, but of course you can, using wavelength, for example. And then you realize that you could put scales on lots of things. For example, how stylish the wardrobe is. You could come up with some scale. And of course, perhaps the most important is the bottom line. How much does the wardrobe cost? And we see that dimensions are nothing other than properties of an object that we can measure. That's all that it is. And so any one of these many various things I've put on this slide could all be the 7th dimension. And that's all well and good, but what I'd like to explain is how do we get from one dimension to another? So I'd like to call this dimension jumping. So I'd like to start from the simplest possible case. So the simplest case is something that's 0-dimensional. So a 0-dimensional object is just a point. Right? So a point. And then to explain the next step, I have my trusty tool here, my father's lightsaber. So imagine that the point is the tip of this lightsaber. And now I want to move into higher dimensions. Well, what can I do? Well, I can do basically anything would be an extra dimension. For example, I could just move it straight down. And what will happen if I move it straight down is that I trace out a line, which is a one-dimensional object. Now if I start with my line, which is just the lightsaber straight up, and move it across to the side like this, then what will I have traced out? A two-dimensional object, a square. And I can do the same thing if I start from a square and I push it over to one side, then what I'll have traced out is a cube. So I can see that I can go from 0 dimension to 1, 1 to 2, 2 to 3, by just pushing over to one side. And I can keep going. I can take the three-dimensional cube, push it in some other dimension, and I get a four-dimensional object, and so on. But what we see here is a hierarchy in the dimensions. 0 is below 1, is below 2, is below 3. And this idea that there's a hierarchy in the dimensions is the central premise in the book Flatland from 1884. So the idea of this book is to represent the various echelons of society by different dimensions. Okay? Point land, line land, flatland, and spaceland. And as you can see from this poster for a recent animated version of this story, that the two-dimensional people are all very nice, that's us, and the three-dimensional people above us are all evil and in control of us. Now, the central character in Flatland is a square. Okay? That's the central character in Flatland. So one of the problems for someone in Flatland is, how do I see in higher dimensions? That's exactly our problem. How do we see in higher dimensions? So how would I imagine doing this process of pushing into another dimension? How could I do that? Well, I could imagine the square coming towards me. I could imagine it coming towards me. And as the square comes towards me, it will get larger and larger and larger till it traces out this object. Right? The square coming towards me will trace this out. And that's a Flatland person's view of a cube, right? Where the small square is the back of the cube and the big square is the front of the cube. You're drawing a cube in perspective. Okay? So that's a Flatland person's view of the third dimension. Now, we're three-dimensional people, generally, but we want to enter the fourth dimension. Okay? We want to imagine higher dimensions. How are we going to do this? Right? Well, we follow the recipe that the Flatland person did. We start with the cube, and we imagine it getting larger and larger and larger. Right? Like so. And what will you have traced out is a four-dimensional cube. Right? That's what you'll have traced out. That's a projection of a four-dimensional cube into our three-dimensional space. That's what that object is that I've drawn on there. And this object is called the Tesseract, or hypercube. Four-dimensional version of the cube that we know and love. And you may have heard of this word Tesseract in other contexts, particularly if you're a fan of Marvel Comics, appeared in recent Avengers movies, causing lots of problems, or if you've seen the movie Interstellar. So in that movie, the astronaut Cooper ends up in some realm where he sees time as a physical dimension. And that is a form of the Tesseract. Now, what you don't see from these pictures is their projections into 3D. They're not genuine four-dimensional pictures. And what happens as you go up in dimensions is that more symmetries can occur. So what do I mean by that? Well, if you take a cube, such as the picture in the top corner there, if I rotate it around, it looks the same. Right? If I rotate it around, it looks the same. Now, of course, with my hypercube, I could have done the same thing, but there are more symmetries that I can't obviously see. For example, this one. So this animation shows you a symmetry of the Tesseract that you can't see obviously in the third dimension. That's coming from a four-dimensional rotation. Okay? So the idea that as you go up in dimensions there can be more symmetries is going to be very important. In particular, it's very important for the seventh dimension. So the idea of symmetry, I want you to keep that in your head, is a very important one in what I'm going to say. Okay, so cubes are, of course, very nice. But you can choose lots of other objects. And one of my favorites is the dodecahedron. Okay, this is a 12-sided shape, pentagons, all of the same area. And you could ask yourself, can I play the same game with the dodecahedron? Can I take that and create a 4-dimensional version? Is it possible? And the answer is yes, it is possible. And what you see is that object. Okay? This is the hyperdodecahedron. It's made up of 120 dodecahedra stuck together. So that's a 4-dimensional version of the dodecahedron right there. I think that's really a beautiful object. Now, of course, you can do many other things. And in the latter part of the 19th century, 4-dimensional geometry became a thing that mathematicians were really interested in. They really wanted to understand it. And so you can see from these old drawings here, someone trying to explain to us what the fourth dimension might look like if we project into 3. And it's from drawings like this that artists were inspired to create new works of art which reinterpret or reimagine what higher dimensions look like. For example, these drawings here. So these are various artists' works where they are inspired by the fourth dimension. In particular, this drawing here is inspired by the hyperdodecahedron. Now, higher dimensional geometry, as I said, sort of became popular in the latter part of the 19th century. But in fact, we can see a description of higher dimensional geometry much earlier in history. In fact, in the work of Dante, in the Divine Comedy from the 14th century. So, what Dante was saying was, halfway through his journey through Empyrean, he said, when I look back at the Earth, I see spheres in front of me, spinning and getting smaller and smaller and smaller as I look back towards the Earth. And if I look up into the heavens, I see spheres in front of me, spinning and getting smaller and smaller and smaller as I look into distance. And that object that he describes, this collection of spheres starting small, getting larger and getting small again, that's a description of a sphere in the fourth dimension. That's what Dante is describing right there. And it might have looked something like this to Dante. Of course, it wasn't animated in Dante's time, but otherwise it might be what it looked like. That's a nice description in words, but is it possible to see this sphere in the fourth dimension? Well, the answer is surely yes. But what does it look like? Well, it looks like this. So if you stand in the center of this sphere in 4 dimensions, you would see a picture something like this. So this, again, is a projection of that sphere into 3-dimensional space. It lives in the 4th dimension. We've projected it down into 3-dimensional space. Now, the reason why I wanted to explain this to you, one of the main reasons, is because there's a close connection to UCL with this sphere in the 4th dimension, because one of the first people to study this geometry in detail was William Kingdon Clifford, who was a professor of maths here at UCL. And aspects of the geometry of this shape still bear his name today. All right, so what have I got to tell you so far is about some of what higher dimensions look like, but I haven't said why 7 is important. I didn't say anything about the 7th dimension. Why is that special? And again, I have my trusty lightsaber at hand to help explain. Okay, so if I move my arm in a plane like this, I hope you can agree that the lightsaber keeps pointing straight up when I do this. But if I move my arm now like this, you see that the lightsaber has changed direction. Right? So something has happened. What's happened when I've done that? What's happened is, in the first case, when I move my arm like this, I'm moving in a flat circle. Right? I'm moving around on a flat circle. And you see that the arrow in that picture is always pointing in the same direction. But what's happening when I do this is that I'm moving around on a sphere when I do that. And as you see in that picture, the arrow can turn as I go around the loop. Right? So we see that there's a difference between going around in a flat circle and going around a loop in a sphere. You get different things happening to the arrow, and this is the concept of holonomy. Okay? So it's the only mathematical jargon I'm going to use is this, so holonomy. So why is this important? Well, when a mathematician sees something like this, you ask yourself, well, okay, when I went round the loop in the plane, nothing happened. When I went round a loop in the sphere, it rotated. What are the possible transformations that could happen to the arrow as I go around loops? What are all the possibilities? And it being a maths problem, it's not surprising that there's a nice ordered list. Okay? There's a nice pattern, but the pattern is not perfect. In fact, there's an exceptional case that happens precisely in the 7th dimension. So what that's telling you is that there are special symmetries that only happen in the 7th dimension. They don't happen anywhere else, only in 7. It's the only way they can happen. And this holonomy, this set of transformations, has a name. It's called G2, like this. So if you don't remember anything else from my talk today, I hope that you remember holonomy and G2. Okay? And that is what I work on. Okay? That is what is my main interest. Okay, so that's all well and good. I explained it in a very abstract way. Can we get some handle on this thing? What is this G2 object? What is it? And for that, I need to go back to the 19th century again. So in the 19th century, in 1843 to be precise, the mathematician Hamilton was walking along a bridge, this one, Broom Bridge in Dublin, and had a flash of inspiration as he was crossing this bridge. He realized that you could define 3 new numbers, and he called them I, J, and K, and these 3 new numbers have to satisfy a certain multiplication rule, which is written up there behind me. And he was so inspired, in perhaps one of the first pieces of mathematical vandalism, he scrawled and cut this formula into the bridge. Okay? So, of course, this was an amazing discovery, to find new numbers. Like, this is something amazing. But of course, why stop at 3 new numbers? Why not 4 new numbers, or 5, or, what's so special about 3? You can try, but you will fail. So if you try to find, say, 5, it won't work. You have to go up to 7 and create something called the octonions. So this is where you have 7 new numbers satisfying a certain multiplication rule. And what is the rule? You can explain it using this picture. So this is the way that these 7 new numbers multiply together. Okay? You just follow the arrows round, it tells you how to multiply. What's amazing is that this is all you can do. You cannot do anything else after this. You try to create 9 new numbers, you'll lose. Can't be done. So there's something very special happening in the 7th dimension. What's even more amazing is that the symmetries of the octonions is precisely G2, that thing that I mentioned on the previous slide. So you can imagine it as sort of the symmetries of this diagram. That is what G2 is. Okay, so now we have sort of a feeling for why the seventh dimension is important. What do we know about the seventh dimension? Well, 7 dimensions is closely related, well, more precisely, the work that I do in the seventh dimension is closely related to soap films and soap bubbles. So something much more down to earth again. So what do we know about soap films and soap bubbles? Well, they minimize their surface area. That's why they form the shapes they do, because they try to minimize their surface area. And you get very special shapes because of that. You get those particular shapes because you've minimized the area. These spaces, these 7-dimensional things with holonomy G2, they also minimize a kind of energy or area. And so they're a bit like soap films and soap bubbles. But unlike the soap films and soap bubbles here in this picture, where we know what they look like, we don't know what 7-dimensional spaces look like. We don't know the answer. So how are we going to find them? Well, you can take your inspiration from the bubbles. And in particular, you can take your inspiration from blowing a bubble. When you blow a bubble, it starts off as some random blob. Right? Just blow it, some random blob, but gradually, over time, it will become a sphere. Right? That's what will happen. As long as it doesn't pop first, right? It will become a sphere. And so you can say, well, why don't I try to replicate that same process? Why don't I start off with some random 7-dimensional blob, pretend that it's a soap bubble, let it evolve through time, and eventually it should become the one with holonomy G2, the one that minimizes the energy. That's the idea. And of course, this process doesn't always work. Just in the same way that when you blow a bubble, you don't always get a sphere. Sometimes it pops. Sometimes it becomes a cluster. Right? Not all of the things in that picture are spheres. Some of them are little clusters. So sometimes it goes wrong, but I was able to show that sometimes this process does work. That you can start with a 7-dimensional object, evolve it through time like a soap bubble, and it does become a space with holonomy G2. But what is this evolutionary process? What is the process that's going on? The process is very similar to the way that heat dissipates around a room. So if you imagine in this picture that the height is how hot the object is, you can see it starts off tall and then spreads out. Spreads out and smooths out. And if we ran it for a long time, it would eventually just spread out and become completely flat. That's how heat moves around. And that's exactly the same thing that happens here. You start off with the random blob, but it smooths out and becomes a sphere. So that's the process that we use. So that's one way in which my work is connected to holonomy G2 through soap films and soap bubbles. But there's another way, and it's using the following picture. So if I draw that picture for you, and I tell you that the lines in that picture are the shortest path between any 2 points, then you'd say, well, they're straight lines, that's a flat piece of paper. That's what you would say. If I draw this picture and say that the vertical ribs are the shortest path between the 2 points, then you would see a sphere. But if I drew this picture, or this picture, and said that they were the shortest path between the points, then something else is going on. There's something else happening. It's not just flat, it's not just a sphere, something else is happening. What that says is that by studying the shapes which minimize length, or more generally, minimize area, I can understand the object itself. So in this situation, I look at one-dimensional objects inside my space that minimize length. What I look at is objects inside 7-dimensional spaces that minimize area. So they're just like soap films. That's what I look at and hope to understand the 7-dimensional spaces themselves. So there are lots of connections between sort of the everyday world and the seventh dimension, and I've hopefully explained some of the things that we know. But what else do we still want to find out? Well, that's very closely related to the work of these two gentlemen, Schrödinger and Einstein. So Schrödinger, as well as his cruelty to cats, was known for his work on quantum theory, right? The very small, electrons, protons, stuff like that. Whereas Einstein is best known for his work on relativity, which helps us to understand gravity. And this divide in the middle was very strict. We do not know how to mesh quantum theory together with gravity. We don't know how to combine these two. This is a central problem in physics that we just don't know what to do. We can understand the very small, we can understand gravity, but we can't understand them at the same time. So, physicists decided to propose a way to combine them, which is called string theory. So what is this? Sounds a bit scary, but all it is, it says, well, look at my picture about quantum theory. If you look at that picture, all of the particles in that picture are just dots. They're just dots, so zero-dimensional objects. What string theory says is elementary particles are not dots, they're not zero-dimensional, they're one-dimensional. They're lines. So for example, they could look like this or this. So just pieces of string, hence the name, string theory. Just says you replace dots by lines. Seems a very innocuous thing to do. But you see, the advantage of having a line rather than a dot is that a line can be curved. Dots can't be curved, it makes no sense, but lines can be. And so you can see geometry starting to appear. And so you can understand that there will now be a possible way to link the very small to geometry, and therefore to ideas in relativity. Now, there's this very serious drawback with string theory. Well, there are two. The first is that you need the universe to have many more dimensions than you're comfortable with. So you have to have at least 10 dimensions for the theory to make sense. If that wasn't bad enough, when I say string theory, there isn't just one. There's like 4 or 5, and they're different. So that's also a pretty serious problem. If you wanted one way to unite the two things, quantum theory and gravity, you'd like there to be one answer, not 5. So, luckily, there's a proposal to resolve this by Edward Witten, who's one of the few people to have won both the Nobel Prize and the Fields Medal, and he suggested something called M theory, or master theory. And what this thing does is it combines all the string theories together into one theory, just one. It unites them all. However, you have to increase the dimension of the universe by 1 more to 11. Okay? And this is the only bit of real maths I'm going to do today. 11 is 4 plus 7. Right? And that's not just numerology, okay? Because those 4 dimensions there, those are our 3 usual dimensions plus the one of time. So we get the 4 usual ones and 7 new ones. And even more surprisingly, these 7 dimensions here are not just some random 7 dimensions, they are 7 dimensions related to our friend G2. So we see that there's a close link between the work I've been doing and the work that many others have been doing in mathematics and to theoretical physics. In fact, recently, there's been a collaboration set up between mathematicians and physicists where we're trying to understand the links and hopefully solve problems trying to unite quantum theory and gravity. So hopefully, I've convinced you today that 7 dimensions are exciting, an interesting and active area of research in mathematics, but it's also closely linked to possibly uncovering some of the mysteries of our universe. And although we know a lot about the 7th dimension, there are still many, many more adventures to be had. So thank you very much.
Thank you, Jason, very much. I hope we have some questions here. We have one at the front.
Looking at your earlier demonstrations of how a two-dimensional being would look 3 dimensions, I can see that, but obviously that two-dimensional person could never experience what we experience in 3 dimensions. Now, the same could go for us, that we are only, well, maybe not fooling ourselves, but saying, well, yeah, that's a representation, but it isn't really a reality. It may be in another being's thing. The other thing I notice is that when you are representing things, they seem to look remarkably like fractals. And I just wonder if there's a connection in any way.
So the question, there were 2 questions. One is that what I'm showing you is not a true representation of higher dimensions, is one way I think you're saying. So we cannot experience it as a higher dimensional being would. And that's true, because all we see are projections. We don't see the genuine 4-dimensional object, for example. But we can still see the reflections of things that are happening in higher dimensions. As I showed you that animation of the Tesseract moving around, that's not a symmetry to us, but in the 4th dimension it is. So we can visualize what's happening in the 4th dimension down with us. The second question was about possible links to fractals. There isn't a link to fractals, but fractals are linked to dimensions because that's where the name comes from. So fractal comes from fractional dimension. That's where the name comes from. So there is a link to dimensions.
Thank you. Any other questions? Oh, we have one here. Mike's just coming.
Is it possible that we could potentially verify string theory? And if so, what experiment would we have to do so?
Yes, so this is, of course, the perennial problem with string theory is that the energies required to do the tests are extremely high, so beyond what currently the Large Hadron Collider can do. However, there are potential experiments that string theorists have come up with that the Large Hadron Collider, if its energies became high enough, they could do. A better approach, in my opinion, is to use cosmological data. So one of the physicists that I've been working with uses data from satellites, so from deep space probes and so on. And that information is more likely to help us verify certain aspects of string theory.
We have a Slido, 2 Slidos.
Okay, 2 questions. What are the applications of this in society? Second question, totally different. Can you have negative dimensions?
Yes, so let me answer the negative question dimensions first, that's a bit easier. So we tend to say that we can have negative -1, so we can have -1 dimensions. And -1 dimensions means nothing at all. So 0 dimensions was something, right? It was a point. But you could say, well, what's -1? That's nothing. Okay? That's nothingness. But you don't go beyond that. You don't say -2, for example. Applications to society. Well, this is, of course, you could ask the same thing, of course, about just particle physics or about many things, about history of art or whatever. There of course, are applications to society in that if it helps us to understand the universe around us, I think that's improving us as human beings. And I think that is certainly something that is worth investigating.
Thank you. Any other questions?
Yep.
One more.
Thank you to whoever asked this question, because I don't entirely understand it, so I hope you do. Why does an 11-dimensional string theory work better than a 10-dimensional string theory? Why is there a limit on the number of temporal dimensions?
Yes. So there were 2 questions there. Why is there a limit on the number of temporal dimensions? And then the other one was about why is 11 better than 10? So let me answer the temporal dimensions first. So there is no, in terms of mathematically, there's no limit. So in maths, you can have as many temporal, as many space as you like. It makes no difference. But in terms of physics, we believe there's just one time. That's it. There aren't others. So that's just a question of physics, not mathematics. Then the other question was about why is 11 better than 10? The reason is, as I said, in 10 dimensions, you have these theories that look different in 10 dimensions. They're actually, in fact, they are different. They're just different. However, they are all projections of one single 11-dimensional object. So they're different projections of that same thing. Because just as a way, if you take a sphere, you can slice it many different ways. And if you slice it differently, you get a different answer. Same thing here, you take your 11-dimensional thing, you slice it to 10-dimensional pieces, you can get different answers. But there's only one 11-dimensional object. That's one way to explain it.
Thank you. Well, it looks as though you've stymied everybody. I think we've all enjoyed it. A wonderful adventure. Thank you, Jason, very much. I'm sure everyone would like to join me in thanking him once more.